If you've ever had to forecast costs for a big investment, a new factory line, a software rollout, anything like that, you run smack into the core fiction of engineering economics. You start by assuming your initial figures are, well, gospel. You assume that machine will cost exactly $100,000, and your rate of return is precisely 10%.
But the real world is just, it's messy.
Yeah.
The future's uncertain, and pretty much every single number on your spreadsheet is a guess. It's a guess based on the best info you had yesterday.
And that gap, right, between the perfect model and the chaotic reality of the market, that's where millions of dollars just vanish. It's where projects die.
Exactly.
Absolutely. So today we're tackling those critical what-if questions. What if that machine actually costs $120,000? What if your sales are 20% lower than you thought?
Or what if inflation doubles? All of it.
We are diving into the structured process for handling all that uncertainty.
Right.
Sensitivity analysis.
Right. Sensitivity analysis, or SA, is really just an analytical procedure. You systematically change the financial inputs, the variables like initial cost, annual revenue, interest rates.
All the guesses.
All the yeses, and you measure the proportional effect on the project's final decision metric. We call that the measure of worth.
And those measures of worth, that's what tells us if the project is a winner or not financially. We're talking about net present worth, NPW, or maybe annual worth.
Or internal rate of return, IRR. Exactly. And it's important to see the difference. NPW gives you the absolute dollar value of the project today, how much cash you're up or down.
Okay.
IRR tells you the maximum interest rate that project can handle before it it financially fails. SA puts all those metrics under a kind of structured stress test.
So, to put it simply, SA answers the question. If my estimate for a key variable is wrong, how badly does that error mess up my final yes or no decision?
That's the core of it.
This deep dive is all about finding those weak points before you put pen to paper.
And finding them efficiently.
Okay, so let's unpack the foundational technique here, the way we play this what-if game. The simplest, most widely used approach is called the one-factor-at-a-time method, or OAT. It sounds almost too simple.
Its simplicity is its strength, especially for that first look. The whole principle is isolation. You hold all the other parameters constant at their nominal or most likely values.
Right.
And you only move one variable at a time to see how the output reacts.
Wait, isn't that a massive simplification, though? I mean, if the price of steel goes up 20%, doesn't the cost of labor usually follow?
It does.
So by testing these things in a silo, aren't we creating these sort of fake, unrealistic scenarios?
That is the method's #1 blind spot, and we will absolutely circle back to that. It's a huge point.
Okay.
But for now, we use OAT to establish let's call it the maximum potential exposure to individual variables. The process starts by establishing your base case.
That's our spreadsheet, the one we believe in, assuming everything goes perfectly to plan.
That's the one. Then, for each critical input, you define the variable range. You decide on a plausible range of change, say plus or minus 15% for material costs.
Got it.
Next, you vary individually. You systematically increase that material cost by 15%, but, and this is crucial, you keep the sales price, the interest rate, the labor costs, everything else fixed at the baseline.
So you're only testing the material cost impact on, say, the total net present worth.
Precisely. You calculate the outcome, you note the new NPW value, then this is the important part, you return that material cost back to the baseline and repeat the whole cycle for the next variable, maybe annual revenue next.
And you just cycle through all of them, one by one.
One by one.
So we end up with this stack of numbers showing us how fragile our projects is to each specific thing. But, to sell this risk assessment to the CFO, you need a visual punch. And that brings us to the famous spider charts.
Exactly. The most common and, I think, impactful visualization is the Cartesian Spider Plot. It's really just a standard XY graph you learn in school, but we use it as a linear sensitivity diagram. It's the best way to compare the relative sensitivity of all the factors at once.
Okay, can you walk us through the layout? What am I looking at?
Sure. On the x-axis, the horizontal one, you have the percentage change in your input parameters, all those variables you just tested, from a big negative change on the left to a big positive on the right.
Right.
The center, at 0% change, that's your base case. That's where all the lines have to cross.
And the y-axis.
That's your measure of worth. Usually it's dollars of net present value.
So we get this series of lines radiating out from the center, one for every variable. This is where the real insight is, isn't it? How do we find the project's Achilles heel in that chart?
You look for the steepness of the slope. This is the key insight we want you to take away today.
The steeper the line.
The more sensitive the project is to that variable. Imagine two lines. One is almost flat, let's say that's salvage value. You could be off on your salvage estimate by 40%, and your overall profit barely moves.
Okay, so you don't worry about that one.
Don't worry about it. But if the line for, say, fuel costs is almost vertical, even a tiny 5% error in that estimate could send your entire project plunging into the red.
That's fantastic. It's an efficiency tool. It tells you exactly which estimates aren't worth spending more time on and which ones you absolutely have to nail down with more research.
It focuses your energy. And you can immediately categorize the variables, too, just by looking at the direction of the slope. Lines moving up have a positive slope. Those are usually your revenue-type variables, like sales price. More is better.
And the ones going down?
Negative slope. Those are your cost-type variables, like raw materials or labor. More of that means lower NPW. It's very intuitive.
Now, the sources also mention a second, maybe less common, visualization. The polar spider plot. A radar chart. Why would we need another type of chart?
That's a great question. The Cartesian plot is all about linear impact. If X changes by this much, what's the dollar change in Y?
Right.
The polar plot is more of a comparative tool. It's better for visualizing the project's overall risk profile, or maybe comparing two different projects against each other. It's a web, like a compass, instead of those linear axes.
So the spokes coming out from the center are the variables, and the rings are the values.
Correct. The spokes are your parameters, initial cost, project life, and so on. The concentric rings show magnitude, from poor at the center to excellent out at the edge. And for SA, we plot the optimistic and pessimistic estimates for each variable on its spoke.
And how does that show sensitivity?
You're looking at the variation distance, the length of the line on the spoke between the pessimistic point and the optimistic point. The spoke with the longest gap, that's your most sensitive variable.
I see.
You're also looking for the shape. A nice, balanced, symmetrical polygon usually suggests that risks and benefits are spread out pretty evenly. That's often the sign of a more stable project.
Okay, so we've run the numbers, we've made the visuals. What does this all mean for the person making the final call? Why is this such a critical tool? I mean, it's the engineer's stress test.
The strategic advantages are, they're huge.
Yeah.
The biggest one is the identification of critical variables. It just cuts through all the noise.
Right.
In a project with 50 estimated variables, SA might show you that only 4 of them, say the interest rate, the price of copper, labor efficiency, and sales volume, actually drive 80% of the risk.
So management can stop worrying about the other 46 things.
Exactly. They can focus their limited research budget where it truly matters. That is pure efficiency.
That immediately saves a ton of time and resources.
It does. And it also enables proactive risk mitigation through something called break-even analysis. By testing these what-if scenarios, the analysis shows you the break-even point or the switching value.
What's an example of that?
Let's say the analysis shows that a mere 7% increase in the initial capital cost makes your net present worth drop to 0.
Okay, that's your breaking point.
That's your breaking point. Now, management knows the exact error threshold, so they can go and proactively negotiate a fixed-price contract with the builder or set aside a contingency fund for exactly that 7% risk before the project even starts.
So it moves risk management from being reactive to being predictive.
Precisely. And it leads to improved decision robustness. Imagine you have Project A. It promises a 20% profit, but it completely collapses if labor costs shift by just 5%.
Okay, high profit, high risk.
Very fragile. Then you have Project B. It promises a slightly lower 18% profit, but it can absorb a 30% swing in labor costs and still be profitable. SA gives you the objective evidence to choose Project B.
The more stable, robust project.
You choose stability over fragility.
And finally, we can't forget the communication part. That spider plot is instantly readable, even for, the non-engineers in the room.
It's invaluable. It's just impossible to ignore that one steep line that's screaming high risk. It lets the engineering team clearly and quickly communicate complex financial risks to the board, to investors, to the CEO. It builds trust because it shows you've considered the worst-case scenarios.
Now, we need to balance this out. We touched on its biggest flaw earlier, but let's really dive into the blind spots. Because traditional sensitivity analysis, especially OAT, has these inherent limitations that can really lead you astray if you trust it blindly.
Right. The core limitation is the one we identified, the independent variable assumption, the silo problem. OAT just assumes that variables change independently, but in the real world, they are constantly correlated.
Could you give us a concrete example of the practical danger there?
Sure. A classic model might test this scenario. Capital costs increase by 15% and revenue stays flat. The analysis will show a catastrophic loss.
Which looks terrifying.
Terrifying. But if the real reason for the capital cost increase is high inflation, then your sales prices would almost certainly increase too, right?
Of course.
By treating them as independent, OAT creates this overly pessimistic scenario that's basically impossible in that economic environment. We might end up rejecting a perfectly good project based on a fake worst-case scenario.
That's a huge flaw, and that leads directly to the next problem, the lack of probability distribution.
Yes. SA tells you the magnitude of the impact, what happens if something changes. But it doesn't tell you how likely that change is to actually happen.
Right.
We might see a project as super sensitive to a 90% drop in market demand, but if the probability of that event is, 1 in a million, focusing all your energy on that terrifying steep line can cause unnecessary panic. It can lead to the irrational rejection of an otherwise sound investment.
So the analysis shows you the possibility of disaster without measuring the likelihood of it.
Exactly. And speaking of panic, when you have a massive project with hundreds of variables, the visualization itself can become the problem. That spider plot can quickly become what analysts call a mess of spaghetti.
Too many lines.
Way too many lines crossing everywhere. It leads to analysis paralysis, where managers just ignore the data, or they focus on the wrong line because it just looks scarier than the others.
And that ties into the nature of the model itself, right?
Yeah.
When we're using OAT, we are running a deterministic model.
Correct. Traditional SA is deterministic. It's based on fixed inputs. It gives you a single static snapshot of risk at one point in time. It is not stochastic.
Okay, hold on. Deterministic versus stochastic. For a manager making a multi-million-dollar call, what's the actual practical difference between those two?
Think of it this way. Deterministic is like drawing one line on a map from point A to point B. You estimate the cost, you calculate the MPW, you get one answer, that's your route.
Okay.
Stochastic analysis, something like a Monte Carlo simulation, is like drawing 1,000 different lines on that map. It randomly tries out thousands of plausible inputs and runs the model over and over, generating a probability distribution of where you might end up. It tells you the whole area you could land in. It shows you that, yeah, your expected MPW is $10 million, but there's a 10% chance it could actually be a $5 million loss. OAT doesn't do that. It just shows you a few fixed points on the map.
To bring this all home, let's look at a case study, a colossal project where failing to do this right had genuinely catastrophic results. The Eurotunnel, the Channel Tunnel connecting the UK and France.
Oh, the Eurotunnel is a classic lesson in underestimating correlation and competitive response. The initial financial model was incredibly complex, and it predicted very high revenues based on specific traffic volumes. That was their base case.
And they did run a sensitivity analysis.
They did, but they focused mostly on internal costs. Labor, construction overruns, initial capital costs, things they felt they could control.
So what was the critical sensitivity failure?
They just severely underestimated their financial sensitivity to competition. They failed to adequately model the what-if scenario of a significant competitive counterattack.
So their OAT analysis.
Their analysis, when they tested ferry prices, it basically assumed that their competitors' fares would stay the same or maybe even go up over time.
And the market responded in exactly the opposite way.
Dramatically so. The moment the tunnel opened, the ferry operators launched this aggressive ferry price war. They slashed their fares to keep their market share.
Oh, wow.
And because the Eurotunnel project was incredibly sensitive to revenue projections, that would have been a very steep line on its spider plot. The lower-than-forecast traffic immediately crippled their finances.
A failure to model that key correlation, your competitor's prices dropping because you exist, sent the whole company into technical bankruptcy.
That's it. They had to restructure billions in debt. A better sensitivity analysis, one that forced them to model the correlated scenario of high competition and lower demand, would have flagged that ferry price war as a critical, high-impact threat that needed a real mitigation strategy.
That is just a powerful illustration of why we move beyond just estimating costs. So, for you listening, here is the core strategic takeaway.
Sensitivity analysis does not reduce your risk. It simply tells you exactly where the risk is hiding. By finding the steepest line on that spider plot, you know precisely where to spend your limited time and your money to gather more data and shore up those critical estimates.
And this brings us right back to the biggest challenge. We talked about how the simplicity of OAT relies on that independent variable assumption, the silo problem. and how it often leads to unrealistic, overly pessimistic models because it ignores correlation.
Right.
So if the goal is truly robust, multi-decade decision-making, the necessary next step for analysts isn't just about identifying which single variable matters most. The critical challenge is figuring out how to effectively move beyond OAT to model and communicate the risk of interconnected simultaneous failures where multiple correlated variables all shift at the same time. That's really the frontier of risk assessment.